Hello, welcome back to physics. We're going to be adding and subtracting vectors using vector components. This is part one of several different lessons. We're going to work a lot of problems like this. So this is really important actually, because in physics we're always adding vectors together. Maybe you have two forces acting on a ball. Maybe you have a rocket thruster pointed this way and a rocket thruster pointed this way, and they're both pushing, and so you have to add the forces together, or the velocities, or whatever you're doing. Almost everything in life is really a vector, so a lot of times you have to add them. Now in the previous set of lessons in the past, we've done vector addition using arrows. We've drawn arrows, we did head to tail, we drew the resultant. That's great for a graphical idea, but it's a real pain to solve any problems, and we don't want to do that in general. So what we're going to do is learn how to add these things together. There really is only one way to add vectors, my opinion. You could probably look up other ways, I guess, but there's only one way to really think about it that makes sense, that's easy to do, and that's bulletproof. That is, if you're ever asked to add vectors together, or if you ever need to add vectors together, add them component by component. What do I mean by that? This vector can be represented as an x component and a y component. You know that. You can split it up. Even if you're given the vector in magnitude and direction, you can still find the x component and its y component. Okay? Then you have some other vector over here, pointed different direction, different length. And this vector can be written as an x component and a y component. Here's how you add the vectors. You just add the x components of the two vectors together. That will be the x component of the final vector. And you add the y components of those vectors together, and that will be the y component of the final resultant vector. So literally, no matter how many vectors you have, instead of writing these arrows and drawing them and then connecting the resultant, all you have to do is break every vector you have into x components and y components. To find the resultant, which means you add the addition of everything, you add all of the x components together. That's going to be the x component of the final answer vector. And then you add all of the y components together, and that's going to be the y component of the final resultant vector. That is why vectors are useful. Because if I have a ball and I throw it this direction, I give it some velocity, I don't want to write equations that are at an angle, that are angled with respect to the ground. So what I'll do is I'll take this velocity and I'll break it into an x component and a y component, and if I have to add any vectors to it, I add the x components, I add the y components, I keep everything separate. So let's put pencil to paper and kind of show you what I'm talking about here. We'll take a simple problem to start, and we'll ratchet up the complexity a little bit, but in general, the idea is really the same. It doesn't really get hard. It's just that you have to get some practice with it. So let's say I have a vector here, and I'm going to do my best to draw it to scale, but it's probably not going to be right. Let's say I have 1, 2, 3, 4, 5. This is 6. And this is 1, 2. So I'm going to put a dot right here, and I'm going to say that my first vector is going to be to the tip of this dot here. So what does this actually mean here? Because I drew it at the intersection here. This means that if this vector is called vector A, right, then that means that the x component of this vector, as I've drawn it, is 1, 2, 3, 4, 5, 6. Let's call it newtons, because everybody can understand forces, right? So the x component of that force is 6. And the y component of this guy, so we'll call this a sub y, is 2 newtons, because it's 2 units up. So when you plot the thing, it's 6, 2, and that's why the thing is right here. So if you wanted to, you could put some dash. Sometimes you see in your textbook a little dotted line here, a little dotted line here. That's fine, okay? So that's vector number 1. Now, I have vector number 2 I'm going to draw next to it, and ultimately I want to add these two vectors together. So let me go ahead and draw vector number 2, kind of in its own coordinate system. I could draw vector 2 on this one, but it would clutter up everything I have, so I don't want to do that. So I'm just going to say that vector 2 is drawn here, that I will draw here. And what I want to do for this one, it's going to be 1, 2, 3, 4 for this example. 1, 2, 3, 4. So 4, 4, I'll put a dot, and I will draw a vector here. And this is the vector I'm going to call my B vector. So this guy is going to be vector B. And I can draw here, so I'll say B sub x is how many units? 4 units, so 4 newtons this way. How many units up? I'll call it B sub y, 4 newtons up, because it's 4 over there. And then for clarity, I can do the same kind of thing. And from the tip of this vector, I can kind of go down here, showing you that it's touching, it's the projections along the axis exactly the same as it was in the previous case. So this vector looks like it's a little bit longer, but it's oriented more horizontal. This vector is angled up more and it's a little bit shorter, okay? But I did not give you the magnitude and the angle of this vector. I didn't give you the magnitude and the angle of this vector. What I'm actually giving you is the x component and the y component of vector A and the x component and the y component of vector B. And now what I want to do is I want to add these vectors together. That's what the plus sign means. So first of all, how would you do it graphically? You could do it graphically. You could measure everything and measure the final result. You get the right answer. How would you do it? Well, I would grab vector B, I'd move him over so it's tail to head. So this is the head of this guy. The tail would probably, just kind of eyeballing it, it'd probably be somewhere like this. And then to find the resultant, I would go here from the origin, the tail of this vector, and I would draw it all the way here. So the vector, the sum of the vectors is going to be something like this, which makes sense because if I'm pulling this way and I'm also pulling this way, then they're kind of in the same direction. They're not quite, but they're sort of in the same direction. So it makes sense that the final vector would be longer like this. But we don't want to do graphical. Graphical's, you know, kind of a pain. So how are we going to do it? What we're going to do is the following. What you're going to say is the vector resultant. That's what I'm calling R. We're saying that that's going to be vector A plus vector B. Whoops. Vector B. The vector R is vector A plus vector B. But more importantly than that, what you really need to internalize and make sure you understand is that the x component of R, the x component of that resultant, is equal to the x component of A plus the x component of B, which is what I told you verbally when we started. And then separately over here, so I'll put, well, I'll just put it like this. For the resultant vector, the y component of the resultant vector is equal to the y component of vector A plus the y component of vector B. So when you see in your textbook, or if your teacher or somebody says you add vectors by components, that's what they mean. They mean you take the x components of the two vectors you have and you add them. That's going to give you the x component of the answer. And you take the y components of the vectors and you add them. And that's going to be the y component of the answer. Now I only have two vectors here, but this process works no matter how many vectors you have. Let's say I have 10 vectors. It's all a bunch of different forces or something pushing on a bowling ball. Well, to find the resultant vector, instead of writing all those arrows, I just add up all the x components. That's going to be the x component of the answer. All the y components, that's going to be the y component of the answer. So the actual math is like crazy simple here. The resultant guy is this plus this. Now in this case, what is the x component of this vector? X component is 6. What is the x component of this vector? That's 4. Everybody knows how to add, right? 6 plus 4, 10 newtons. So that means the final resultant vector is 10 units in the x direction long. Now, for the y components, the y component of A is 2, and the y component of B is 4. Everybody knows how to add, so you see physics isn't that hard. If you know what to do, it's just addition, 6 newtons. So what I want to do now is I want to draw this. What would this look like to, number one, show you how you put it all together, and number two, prove to yourself that it actually does add these vectors together. So what does the resultant look like? If I draw the summation, which is the resultant vector here, what do I get? X and y. We're saying the x component is 10 units long. So let me go and we'll do it in blue just to keep it separate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're 10 units long that way, 6 units up. 1, 2, 3, 4, 5, 6. So I'm going to try to do my best to put a dot. 10 units in x, and then 6 units up. And so what I'm going to get, hopefully if I can draw a straight line, that's not a straight line. But anyway, you get the idea. It's pointed straight like this, and then if you project down, the resultant x is 10 newtons. And if you go over here, the resultant y is, what was it, 6 newtons, right? And this vector is called the resultant vector. And the resultant vector has components 10 units long in the x direction and 6 units long, 6 newtons long in the y direction. Now notice, does this, I know that the scale isn't exactly right on my tick marks and all that stuff, but does this kind of look like it could be the addition of these two forces? The answer is yes, because this is like a rope pulling with this strength, and this is like some rope attached to the same thing pulling with the same strength. These guys were kind of lined up more or less in the same direction. This one was higher, but it was more or less the same direction. So we expect the resultant to be kind of in that direction. That's what it is. And we expect it to be longer than either one because, again, they're both kind of in the same direction. They're not exactly lined up, but they're kind of pointed that way. And then mentally, if you take this guy and do the vector addition graphically, we already said that the vector should be something like this. If you can mentally come down and look at that, that's exactly what we've drawn. So this resultant is exactly what you would get by the graphical method, but you don't have to draw any arrows. We're doing a lot of arrows here just to show you what it means, but really, you don't have to have any of these arrows. All I have to do is say x component plus x component, that's the x component of the answer. Y component plus y component, that's the y component of the answer. Once I have the components of the resultant, that's all I need to express the resultant in terms of a vector. Now, I can say the x component is this and the y component is this of the resultant. That's totally fine, but usually you want to express your resultant vector in magnitude and direction, because remember, there's two ways to write a vector. You can write it in components, that's totally valid way to write a vector. But you also want to write it, or you can write it, in terms of the length of r and then the angle. In other words, the length of r is given as drawn right here, the length of that arrow, the angle from the positive x-axis. So if I want to express this in components, I've already done it. In fact, I can even circle these and say, well, this is the x component, that's the y component, that's the answer, that's my vector. But maybe I want to express it in the length of r and the angle. How do I do that? The last couple of sections, that's all we've been doing over and over again, and that's why we cover that first, so I could teach you that. Now when you get to this, you'll do this other stuff first to add the vectors, and let's convert it to magnitude and direction. All right, so the magnitude of this resultant vector, which is the length of the vector, we do exactly the same as we did before, Pythagorean theorem. The x component was 10, the y component was 6. So under here we have 10 squared, because it's Pythagorean theorem, and it's 6 squared. Like this. So under here we have 100 plus 36. So what we have is the square root of 136. So what do we get as an answer? The resultant vector, the length of it, that's what these bars mean, that means the length of it, is 11.66 newtons. That's what happens when you take 136 and take the square root. Notice it's 11.66. That is longer than this looks. I mean, I didn't give you the length of A and B, but you can see the x and y components. It's longer than any one of those, which makes sense, okay? Now let's find the angle. What is this angle? The angle is found as, what? You write it as tangent of the angle is the y component divided by the x component, opposite over adjacent, right? Well, now we're growing up a little bit. I don't have to write tangent of angle equals this and then show you the inverse tangent. I'm just going to show you that the angle is going to be equal to the inverse tangent, -1 of the y component over the x component, which means it's the tangent, inverse tangent I should say. Y component was 6, that's going to go on top, 10 is going to go on the bottom. So it's going to be 6/10. So when you take 6 and divide it by 10, it's going to give you 0.6. And you take the inverse tangent, what you're going to get is going to be 30.96 degrees. Always, always, always. When you take the inverse tangent, to get an angle back, check and see if this angle makes sense with your drawing. You go back here, does it make sense that this is a positive 30.96? Well, I've drawn everything. I expect this angle to be a positive angle measured from this axis, and it's about 30-something degrees. So this angle is 30 degrees, 30.96 degrees. So it makes sense. So I don't have to add 180 or anything because the answer I got back from my angle matches with what I know the problem is telling me. So I'm done. If I were to get an angle back, like at a different problem, that were totally on the other side of the coordinate system from where I am, then I'd have to add 180 degrees to get the angle correct for my problem. But in this case, everything was right. So let's go through the process real quick, and we're going to do one more. I give you vector A, I give you vector B. So far in these problems, I'm actually just giving you the components to start with. How do you find the resultant? You just add them up. Add the x components together, you get this. Add the y components together, you get this. I can plot it just to prove to myself, but I don't even really have to plot it because this is the answer to the vector summation. Now, if I want to turn it into a magnitude and direction, I use Pythagorean theorem on these, as I always get. I get a length of 11.66 newtons. And to get the angle, I do the inverse tangent of y divided by x. Always the same thing. Check to make sure the angle is correct. It is correct, so these are the magnitude and direction. These numbers express where the vector is pointing and how long. And these numbers are a totally different but totally valid way to express which way that vector is pointed as well. Okay, so now in the next problem, we're going to do the same thing, except I'm going to, instead of drawing everything first, I'm going to actually give you the components first. I'm going to say you're given the following. The x component of vector A is 2 newtons. The y component of vector A is 3 newtons. I'm also going to give you that the x component of vector B is negative 3 newtons, and the y component of vector B is 1 newton. Okay? So what I want to do in this problem is I want to draw everything to kind of get a good feel for it. I want you to add the vectors together, and I want you to tell me, I'm sorry, not add the vectors, we're going to do something a little bit different. Instead of adding the vectors together, which you could totally do, I want you to find the subtraction of the vectors. I want to find the vector subtraction. Remember, we did that graphically, right? So we know we can add vectors and we know we can subtract them. In the previous problem, we just added components together. And if we want to find the vector sum here, how do we do it? I mean, you can just look at it. You can see this plus this is going to give me the x component of the final answer. This plus this is going to give me the y component of the final answer. So if we add components together to get their vector sum, what do you think we do if we want to subtract vectors? Well, we subtract their components, right? So that's very, very, very much in line with what you would expect, okay? So how do we find a minus b? We're going to end up subtracting the x components of the a and b vectors, and we're going to subtract the y components of the a and b vectors. But before we get there, let's just take a second to draw these vectors. I always recommend you draw stuff for your problems. So I'm going to draw this to make sure that we're on the same page. For the a vectors, it's 2 for x and 3 for y. So 1, 2, 1, 2, 3. So put a little dot right there. 2 for x, 3 for y. So I can draw this guy to the, I didn't even really draw it to the origin. It's kind of sloppy. You got this guy right here. And I'm going to tell you that this is vector A. I just don't want to clutter it by writing it down there, vector A. And I can draw a little dotted line, and so I can show you that this is a sub x is 2 newtons. And I can draw a little dotted line here, and I could say that this is a sub y is equal to 3 newtons. You know what? I'm not going to put the newtons here because I don't want to clutter up my drawing. You'll see why in a second. So that's AX and AY. So this is 2 newtons, this is 3 newtons, right? Just as I have it drawn. Now what is going to be, let's switch colors to red. What is going to be the B vector? Well, it's negative 3 in X, 1, 2, 3, negative 3 in X, and only up 1 positive for Y. So that means I can put a dot right there, negative 3 comma 1. And I'm going to draw a vector like this, and I'm going to call this one the B vector, like this. And again, I'll switch components, and I'll say this is b sub x, call it, go ahead and write this one down, negative 3. And I could go over here. This is going to be b sub y over here. So I can, going to kind of clutter my drawing. B sub y is 1. You see why I don't want to write everything down because it gets confusing. But the bottom line is you have an a vector and you have a b vector. The a vector is defined by these two numbers, 2 comma 3. That's why it points that way. The b vector is over here, defined by negative 3 for x and 1 for y. That's why it points over here. Okay, so we have the drawing here. Now, we were not asked to add these vectors together, but if we were going to add them together, it would be simple. We would just take this plus this, and then this plus this, right? But what we just told you here a second ago is that the resultant vector, I didn't want to add them. In this case, I want to subtract them, a minus b. Now, before we actually do the subtraction, do you remember how we did it graphically? How did we do it graphically? We said, well, when I subtract a vector, that's the same thing as adding a vector, but I flip the direction of that second vector. That's how we did it graphically. So let's go over to the side here for a second. I'm actually trying to decide. Let's go over here, because we're not going to use this board at all anymore. Let's go over here. Let's add a, well, you know what? Let's stay over here, actually. I changed my mind. Let's do a minus b. So if I'm going to do a minus b over here, the a vector is exactly the way it's pointed. So this is the a vector. I'll try my best to kind of make that parallel. So this is the a vector. And this is the b vector. But we're not adding b, we're going to add minus b because we're going to be subtracting it. So minus b means we flip it around and I can just put it right there. So I'm going to try my best to keep that about right. So this is the minus b vector. Again, this is b pointed this way. Minus b just means we point it in the other way, and then I grab him and I move him head to tail, like this. So that subtraction then becomes addition. So then the addition of these two vectors is we draw just like this, and this is called a minus b. So that's how we do it graphically, right? How do we do it by components? Well, we just say the x component of the answer is going to be the x component of a minus the x component of b. Whoops. B sub x. And we'll just go ahead and do it right now. We'll say the x component of a was 2, and the x component of b was negative 3. So it's 2 minus from here. But this component actually was negative, so we have to wrap it in parentheses to make it a negative 3. We're subtracting from here the negative 3. So the x component here, minus a negative means plus, so you're going to get 2 plus 3 is 5 newtons. That means the answer of these two things, when you subtract them, points 5 units along in the x direction. All right, so let's switch colors and do the y component. The y component of the resultant is going to be the y component of a minus the y component of b. The y component of a was 3, y component of b is 1, so 3 minus 1. And so you all know the answer to that, so it's going to be 2 newtons. So I can circle these. That is the answer. That's exactly the answer, 5 and 2. So the answer here is 5 units to the right, 2 units up. Let's draw that and see if it kind of makes sense with what we drew here. If I go down here and just draw a little coordinate system, let's say 1, 2, 3, 4, 1, 2, 3, 4. I guess I need a little more here. So what I'm saying is I have the resultant is 5 units in x, 1, 2, 3, 4, 5, and 2 units up, which means I'm right around here. So if I draw that here as straight as I can, this is the resultant vector. It looks an awful lot like what we did with the graphical method. It is the same thing. Of course, I'm doing everything freehand. So the stuff you learn in the graphical method is totally fine, but the component method is much, much, much more powerful. When you want to add two vectors together, you add their components to get the answer. When you want to subtract two vectors, you subtract their components. And the answers you get for the x and y components are the coordinates that define the tip of that vector resultant, right? Now, this is a totally valid way to write the resultant vector a minus b, the x component and y component. That is a totally valid way, but a lot of times they'll tell you, I want you to give me the answer in magnitude and direction. Again, that's why we practiced it before. So let's go over here and say, let's find the magnitude and direction now. Rewriting what we had before so I don't have to kind of slide the boards all the time. The x component was 5 newtons, and the y component of the resultant was 2 newtons. So I don't want to rewrite everything. So how do I find the length of the vector r? Pythagorean theorem is your friend. X component's 5 squared, y component's 2 squared. So what I'm going to have is 25 plus 4 square root 29. And so the resultant magnitude is square root of 29. What do I get? 5.39. So that is how many units of force is pointed obliquely as a combination of x and y, 5.39 newtons. All right, and now I want to find that angle, right? So the angle is always an inverse tangent. It's always the inverse tangent of the y component divided by the x component. So this angle, theta, is always the inverse tangent of the y component divided by the x component, right? The y component here is 2. The x component of the answer is 5. So it's 2/5. So it's going to be the inverse tangent of 2/5. When you divide that, you get 0.4. So if you go in your calculator and you type in 0.4 and take the inverse tangent, the angle it's going to give you is 21.80 degrees. Then you always see, okay, when I get angles back, I've got to check to make sure they're right. This means a positive angle of 21 degrees is measured up from the x-axis. 20 degrees, that's about right. Certainly it's not way over here. If the angle were way on the other side, then I'd have to add 180. So I always get my angle, I always check it with what I have, and then I make sure that I'm right. And so in this case, it is 21.8 degrees. Of course, it's measured, implied that you're always measuring it from the positive x-axis, unless you specify otherwise. And the length is 5.39 newtons here. So this would be a case where I have a vector A, and I'm not adding b to it, I'm actually subtracting b to it, so from it. So it would almost be like somebody pushing this way, and then somebody pulling, which means you're subtracting in the other vector there. So we define A, we define B, we're going to subtract the two, which means we flip B around, and we draw our resultant. That's the graphical way. The component way, you just add or subtract the components as usual. So I hope you can start to see why we spent so much time introducing the concept of a vector. And then we introduced the concept of components of a vector, x and y components. And then we did a bunch of problems with how you break a vector into components, because when you add vectors, you always add them by components. So once you get the answer in component form, then a lot of times you want to convert back to magnitude and direction, or magnitude and angle, right? Which is what we've done in these problems. So far for these problems, you've done real vector addition, but I've given you the components. I gave you x and y for A and B. I gave you x and y for the other problem for A and B. I gave you the components to start with. When I started off the very first thing, I drew these vectors, I gave you the components. Now in the next couple of problems, I'm not going to start off by giving you the components. I'm going to give you the length of vector A and its angle. And I'm going to give you the length of vector B and its angle. And I'm going to tell you to add those things together. So you're going to have to know, this is the one thing that's kind of hard about physics at first, is no one's going to tell you what to do. They're not going to tell you to break A and B into components and then add the components. You're going to have to know, he gives me magnitude and angle. I'm going to have to make those into components, right? Once I have them into components, x and y, I can add the x's and I can add the y's. And then when I get that, I can convert back to magnitude and angle. So we're doing all of these little skills separately because in the next problem we're going to put them all together, and you're going to find out that because you know each little step, working a full problem start to finish isn't a big deal, and you'll have practice and confidence in it. So let's go ahead and do that right now.